This beast is a 12th degree polynomial. I mean, just look at it. We're talking 13 different terms with coefficients that just skyrocket into the trillions. And our goal is to find the values of x that make this whole crazy thing equal to 0. So, yeah, where do you even start with something like this? I mean, seriously, trying to brute force this? Totally out of the question. You're not just going to guess your way to the answer. This isn't a problem you can just muscle through, you know? It's more like a puzzle, and it needs a very, very specific key. And that, right there, brings us to our elegant weapon. See, when you're up against a monster this complicated, a bigger club just isn't going to cut it. Nope, you need a smarter, sharper tool. One that's designed to find its hidden weakness. And that tool is a really clever theorem from Murad Sultanizudi. Now, what's so cool about this is that it doesn't even try to solve the equation head-on. Instead, it's kind of like an X-ray. It lets us see the hidden structure inside the polynomial. And the way it does this is by calculating a whole new set of numbers, these S values, that actually reveal the monster's true, simpler form. Okay, so we've got our weapon. Now it's time to put the plan into action. And this isn't some chaotic flash of genius, by the way. It's a really methodical, step-by-step process. The plan itself is actually pretty straightforward, even if the math gets a little intense. So here's what you do. Step 1. You use the theorem to set up the calculation for that first new coefficient, which we'll call S sub 0. Step 2. You take all those giant original coefficients and plug them into the formula. Then you just crunch the numbers. And the last step, you just do it all over again. For S1, S2, S3, all the way up to S11. Now, I know what you're probably thinking. Wow, that sounds really tedious. And you're right, it is. Here's the thing. As the calculations were getting done, something absolutely incredible started to happen. A kind of surprise collapse, something you would never have predicted just by staring at that original monster of an equation. So after all that number crunching, the very first calculation for S sub 0 is finally done. And the result is 0. Yep, just a big fat 0. Okay, well, that's interesting. But, you know, maybe it's just a coincidence, right? I mean, one number out of 12 turning up 0 could be a fluke. But of course, the process keeps going. So the big question is, what about the next few? What happens with S1, S2, S3, and S4? They are also 0. Every single one of them. And suddenly, okay, this is definitely not a coincidence anymore. This is a pattern. A really strange, really powerful pattern is starting to emerge from all that chaos. All right, let's just cut to the chase and look at the whole shebang. Here are all 12 of those new S value coefficients all laid out. Just look at this. S0 all the way through S4, 0. Then, bam, we get a big non-zero number for S5. And after that, more zeros, right up until the very last one, S11. Think about that. Out of 12 of these super complex brand new coefficients, 10 of them just collapsed. They vanished into 0. This right here is the monster's Achilles heel. So the big question is, what does all this actually do for us? I mean, it's a cool pattern for sure, but how does it help us solve that original problem? Well, it changes pretty much everything. See, the theorem lets us completely rewrite that original polynomial, but using these new S values instead. And since most of them are 0, they just disappear. Poof, gone. Just look at this transformation. Before, we had our monster with 13 terms. And after, we have this clean, elegant, beautiful equation with only 3 terms. The monster has officially been tamed. So why is this such a big deal? Because this new equation, it's not really a scary 12th degree problem anymore. If you squint at it just right, you'll see it's actually just a quadratic equation, you know, from high school math. It's just in terms of x to the 6th. And that's a structure we know how to deal with. The problem has been totally transformed from impossible to, hey, we can actually do this. And that right there is the prize at the end of the road. We can solve this much simpler equation to find the 2 possible values for x to the 6th. And once we have those, it's a straight shot to finding all 12 of the complex roots for our original monster polynomial. We did it. We found the solution. So the big takeaway here is really powerful, right? The solution was never about just grinding it out. It wasn't about being a human calculator. It was about finding the right tool, a different perspective that let us see the beautiful simplicity hiding underneath all that terrifying complexity. And that kind of leaves us with one last question to chew on. Sure, this was a mathematical monster, but the principle, that applies just about everywhere. It makes you wonder, right? What other huge, complex, intimidating problems out there in science, technology, maybe even in our own lives have an elegant, simple solution just sitting there, hiding in plain sight?